Hello again everyone, welcome back to ptet.chemistry channel. My name is Dr. Ant. In this tutorial video, I'll go through this pure chemistry, part of the triple sciences for the 14 to 16 years old students. This is on the periodic table chemistry, considered to be one of the driest and one of the most boring contents in the whole of chemistry, partly because people find that it's a lot of things to memorize, but then in the series of lecture tutorials on this topic in particular, which is happened to be my specialty, so I specialize in inorganic chemistry, so basically I find it a lot interesting. There's a lot of very cool stuff which you can see from the trends which I will show you throughout this journey. So let's get started. In the first bit, we're going to look at the arrangement of elements, because the periodic table obviously arranges the periodic table in terms of periods. So periods is going across, so it says basically going horizontally like that, and there's called periods. And then you have groups are going vertically, so this is up and down, so this is vertically, and then this is basically how they're arranged. You also have increasing proton number or atomic number. So from the topic of atomic structure, proton number or atomic number, it tells you the number of protons. And where are the protons? The protons are in the nucleus of an atom, and as such the nucleus of an atom is going to be positively charged, as it has the protons which are positively charged and the neutrons which don't have any charge at all. We're going to describe the change going from left to right across a period. They go from metal to non-metals. If we look at this cutout of the periodic table, which is slightly different from the periodic table you will get in an exam, what you have there is period 1, so there's the first shell, period 2, the second shell, period 3, and so on and so forth. And then you also have this group 1. We use this Roman numeral. We cannot use the normal numbers like this for the group number, as these are the standards that have been passed down from the previous generations, and so on and so forth. So we know that group 1, 2, and 3 are what you consider metals in general, although they classify boron as actually non-metals because of this line here, this kind of like lines which are not given to you in exam. So I'm just going to draw this thing in red a little bit, highlighting that in red a little bit. So everything below these lines, they are considered as metals, including this middle block, which you call transition elements. Transition elements are also known as transition metals. All of them are elements, all of them are metals, so all of them have giant metallic structure, because metals have giant metallic structure, where you would describe the metals as, how do I draw this? Layers of cations. They're all of the same sizes, as these are elements, therefore they contain only one type of atoms, which of course delocalize the outer shell electrons so that they have a fully filled outer shell for their ions. So these are your delocalized valence electrons, and you have a sea of them, you have a bunch of them, and these are your cations. That is what you call giant metallic structure there. And all of these, including the transition metals, the group 1, the group 2, and part of the group 3 metals. And some of these metals further down in each group, as you could see, they go from non-metals to metallic, non-metals to metallic. So what I could say is they become more metallic down the group, more metallic down group 3, group 4, group 5, and group 6. But then we also know that they become more metallic from left to right. So more metallic across a period as well. So these things are not to be memorized like that, but it's really just common sense, as you go from metals on the left to non-metals on the right, as you go from non-metals on the top of the group 3, group 4, group 5, to things which are more metallic, like aluminum is metallic, tin and lead are metallic. You don't deal with bismuth or antimony or polonium, for instance, which is radioactive, but then these are metallic as they have more metallic character compared to their non-metals further up in the groups. Then describe the relationship between group number and the charge of the ions formed from elements in that group. We know that group 1 metals like to lose one outer shell electrons. And if I go straight to the points of interest, which will come back in a little bit, Where am I? I am talking about, I tell you what, let's just go through the points of interest straight away. As I did mention, horizontal row of elements is called a period, so that's going across a period horizontally. Vertically, we are talking about group 1 all the way to group 8. We know that from atomic structure, group number tells us how many outer shell electrons there are. So valence shell means outer shell electrons. So how many electrons do you have in the outer shell? It means the exact same thing. Okay. Period number, how many shells get occupied? How many circles do you draw for the shells? For instance, when you have lithium, sodium, potassium, so lithium would be 2, 1 because hydrogen and helium is in the first shell, so 2, and then after that you have to go to the new shell. So lithium, the second shell, 1 electrons. First shell is full, second shell 1 electrons, so outermost shell 1 electrons, there's group 1 there. And then you have beryllium, which is 2 because you need to go to the next element in order to fill up the electrons like that. Of course, then you could also have sodium, which will be 2 going across hydrogen and helium. Lithium to neon is 8 in the second shell, and then that is not yet sodium. You need 1 more to reach the sodium, so that's why sodium is in the third period. First shell, second shell, and third shell. First, second, and third shell, because period number tells you how many shells you need to occupy, first, second, and third. The group number, group 1, tells you how many electrons there are in the outer shell. On the other hand, when you have beryllium is just, not beryllium, but magnesium. It's going to be 282, for instance, because 2 in the first shell, 8 in the second shell, and then 2 in the third shell to go to magnesium. So things like that, okay, is the reasons why I can kind of show you what is happening there. So lithium, sodium, and how about if I do potassium as well? So potassium is 2881. Not really a lot of space there, but you get my drift. My drift really is to just show you very briefly. Oh, run out of space there. Just you could see that the first shell, the second shell, the third shell. So first shell, second shell, third shell, and last but not least, the fourth shell, because potassium is in the fourth period. And all of these are quite special because all of these are 1 electrons in the outer shell, because all of them are group 1 metals there. Noble gases are your group 8, so they are the inert because unreactive chemically, and the reason they are unreactive is because they already have a fully filled outer shell. But then why did I say think of helium? Because when you have helium, you do not have 8 electrons in the outer shells. So even though it's group 8, but then helium only has 2 electrons in the outer shell. So be very careful about helium, because helium only 2 electrons in the outer shell. This is one of the most common trick questions in multiple choice, because students think group 8 means 8 electrons in the outer shell. That is not true. It just means that you have a fully filled outer shell. That's what makes you unreactive, because your first shell maximum is 2 electrons. That's why helium has a fully filled outer shell. It's a noble gas, even though it's in group 8 there. Valency, we talk about valency when we talk about combining power of elements. Whether you're metal or non-metals, you can lose electrons for metal. You can gain or you can share electrons for non-metals. Gaining or sharing electrons are very common properties of non-metals depending on what their partners are. We talk about metals losing electrons, and therefore they will form cations or positive ions, and the purpose is to get a fully filled outer shell. As I did mention earlier, we talk about the non-metals. The non-metals gain electrons, but it could also share electrons. When you gain electrons, you form negative ions. The purpose is still the same, fully filled outer shell. Again, when you share electrons with other non-metals, so non-metals and non-metals, they will form covalent bond. So they share electrons with non-metals, and as a result of that, they'll form covalent bond. And the objective is the same thing. You want to get to a fully filled outer shell. That is always the main objective of bonding. Why do you bond? To get to a fully filled outer shell. Why do you not bond? Why do noble gas not bond at all? Because you already have a fully filled outer shell. Now, some groups have very special names. Group 1 are specifically called alkali metals, which we will come across eventually again, why it is such. And group 2 are called alkaline earth metals. Now, the alkaline metals is your case study. The alkaline earth metals are not exactly a case study. It's just that I want to show you the difference between the two names here. Then you have halogens. This is another case study. Halogens are the group 7, and the noble gases are the group 8. Even though they are in group 8, not all the elements have 8 electrons in the outer shells. Think about helium, neon, argon, krypton, etc., etc. What is so special about them? Fully filled outer shell. Outer shell is also known as valence shell. So if you want, you can say fully filled valence shell, fully filled outer shell there. This is like properties of the elements. Sodium all the way going to argon. This is period 3 chemistry. Period 3 chemistry happens to be your case study, so you need to know everything about these things here. Now for the period 3 chemistry, we know that what we have is sodium. So sodium element is Na, magnesium is Mg, aluminium is Al, silicon is Si, phosphorus is P, sulfur is S, chlorine is Cl, argon is Ar there. We might not use this 0, we use VIII for group 8 for the noble gas instead. How many outer shell electrons? Outer shell electrons, that is called the valence electrons. Depends on your group number, so that follows your group number. But then your combining power is slightly different. When I talk about combining power, well actually, I can show you the valency shown in that compound. We go straight to the noble gas first. So no valency for the noble gas is basically 0 because it doesn't want to form any bonds at all. It doesn't want to lose, does not want to lose, does not want to lose, or gain, or share electrons in order to complete outer shell because it already has a fully filled outer shell. So it doesn't need to do anything. Therefore, it's chemically unreactive. In terms of group 1, group 1, group 2, group 3, so these are metals. And you talk about metals losing electrons. How many to lose? How many electrons to lose? To complete outer shell. That is the key focus there. And that is why you get your combining power of metals as 1, 2, and 3. These are the number of electrons you have to lose to get to Na+, Mg2+, Al3+, and that is why you classify this as metals there. On the other hand, you have silicon onward to chlorine, which silicon is like metalloid, so you do consider it like in between characters of metals and non-metals. In the US, in the United States, a lot of there is a place called Silicon Valley. That is the place where a lot of technology hubs are there, technology companies like Google, Apple, Facebook, etc., etc. That's because a lot of computer chips, they all use silicon chip. Silicon is a semiconductor. Silicon is a semiconductor, very, very, very important semiconductor industry. If you do gaming, if you do processor, computer kind of geek kind of stuff, you will know that silicon is in every single chips and graphic cards, etc., etc., even in the hard drive like SSD or hard disk drive, etc. Okay, so it is semiconductor, but not as well as this reactive metal, but at least it's not a reactive metal. And it has a structure similar to diamond, so it has quite high melting point. You see, it has a structure similar to diamond actually. And so what I can comment on this is similar to diamond. When I say similar to diamond, diamond is your case study, so that is your giant covalent structure. Structure is not bonding, structure is structure. And of course, then you need to break many strong covalent bonds in order to melt or boil silicon as an element. But silicon tetrachloride, SiCl4, if you think about CCl4, CCl4 is covalent like this. So carbon form 4 covalent bonds, chlorine being group 7, they form one covalent bond to complete the outer shell. Now I'm going to replace the carbon with silicon, and this is SiCl4. Carbon is above silicon. Silicon is below carbon. Covalent, 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 covalent. SiCl4 is covalent. So SiCl4 is no longer ionic, and SiCl4 is covalent. And you will see the division between the oxide and the chloride. So be very careful. This is oxide. This one is chloride. So we need to be extremely careful what we are saying there. So the metal oxides, Na2O, which they don't give you the formula of the oxide. I'm just going to write it in. The formula of the oxide is Na2O because of Na plus O2 minus. This is year 9 chemical formulation based on the charges of the ions, give you the valency. And then when you do the crisscross, you're going to get 2 of the Na plus and 1 of the O2 minus. Na2O is a basic oxide. It's the oxide of metal. This is MgO. So these two are what you call basic oxide. Aluminium oxide is very special, amphoteric. Al2O3, better write it down somewhere. Al2O3, Al3 plus O2 minus. Case study electrolysis of Al2O3, dissolve in cryolite to help lower its melting point. That's how you extract aluminium from bauxite, which is Al2O3, the main ore inside bauxite. Amphoteric oxide reacts with both acid and also bases. Silicon oxide, SiO2, and then phosphorus 5 oxide, P4O10, but phosphorus can also exist as phosphorus 3 oxide, which is P4O6, so be aware of that. You have SO2 and SO3, two different oxidation numbers, just like P4O6 and P4O10. This is sulfur plus 4, sulfur plus 6, plus 4 and plus 6 refer to oxidation numbers. So we have sulfur plus 4 oxidation number, and we have sulfur plus 6 oxidation number. SO2 going to SO3, part of the contact process under the equilibrium topic as part of the case study. One of the most famous case study in contact process, SO2 plus O2 reversible reactions in equilibrium with SO3. The oxide of chloride is also acidic. These are all non-metal oxides. Non-metal oxides are acidic. Metallic oxides are basic. Apart from this Al2O3, which is amphoteric. In all of these oxides, as well as all of these chlorides, which you can get the formula of, and then what you get is these valency shown in the compound, Na plus Cl minus, so the Na is 1, 2, and 3, based on the charges of the ion, Na plus, Mg2 plus, Al3 plus. How many electrons do you lose in order to complete the outer shell? Silicon tetrachloride. How many electrons do you need to share? So silicon has 4 outer shell electrons, and therefore you need to share 4 electrons in order to complete your outer shell there. Therefore the valency is 4. I put down pH3 instead of PCl3, but if I want, I could have changed this to PCl3. Then that is 3 electrons there. But then PCl3 could also be PCl5, so better to just stick with pH3, where the phosphorus is light. Think about ammonia, where the nitrogen, group 5, want to share 3 electrons, form 3 covalent bonds to complete the outer shell. H2S, think about H2O. The oxygen forms 2 covalent bonds. If you know ammonia, you also know water. So that is your ammonia, where the nitrogen forms triple covalent bonds. And then this is water, where the oxygen forms 2 covalent bonds because you have 6 electrons in the outer shell. Complete the outer shell by sharing 2 electrons by forming 2 covalent bonds there. HCl, hydrogen chloride. So hydrogen chloride is not hydrochloric acid, so be very careful. Hydrogen chloride, so chlorine with 7 electrons in the outer shell. This is part of year 9 chemistry content. So this is year 9 under dot and cross, chemical structure and bonding, covalent bonding. Candidates should be able to draw the dot and cross for all of these simple covalent structures, including hydrogen chloride, present as a gas, simple covalent structure, low melting and boiling point. Chlorine forms single covalent bond there. They share 1 electrons to complete its outer shell there. And argon, again, zero valency because it doesn't form any covalent bond. It doesn't lose electron, doesn't gain electron, they just have valency of 0. Now in terms of metallic character, going from metal to non-metal, and in terms of the melting point and boiling point, talk about structure, giant metallic structure, where you have these layers of cations surrounded by sea of delocalized valence electrons, strong metallic bonds to be broken, and that is the reason why your melting point, you see, sodium, magnesium, aluminum increases. Silicon has a giant covalent structure. How does silicon look like? Just like in diamond, so each silicon is bonded to 4 other silicons, and then the silicon is bonded to 4 silicon altogether. So giant covalent structure, many strong covalent bonds to be broken to melt silicon. Phosphorus, sulfur, chlorine, and argon, these are what you call simple covalent structure. So what you have is P4, S8, Cl2, and argon. These are what you call molecular formula. Molecular formula is part of year 9. Year 9 under chemical formula and equations. It is defined as the actual number of atoms in one single molecule. So what you have there is the phosphorus P4 is an unusual structure, so it's a tetrahedron where there are 6 times phosphorus single bonds. Of course, if you miscounted, you might think P4 has 4 covalent bonds, but that is not true. Phosphorus forms 3 covalent bonds there with lone pair on each phosphorus. 1, 2, 3. Let me count it and color it so you can follow. 1, 2, 3, 4, 5, 6. So there are 6 times phosphorus single bond there. As for S8, so this is P4. How about S8? S8 you get like a W like this, and then another W at the back there. You will get 1, 2, 3, 4, 5, 6, 7, and 8. So what you get there is sulfur on each of the pink region there. And just like oxygen, sulfur forms 2 covalent bond on each sulfur. So that is S8. And in S8, you have exactly, I think, 8, if I'm not mistaken. Let's count. So you have 1, 2, 3, 4, 5, 6, 7, 8. So you have 8 times sulfur covalent bonds in S8 molecule. Cl2 is pretty self-explanatory, diatomic molecules from your dot and cross, year 9 simple covalent structure. Candidate should be able to draw diatomic dot and cross for the halogen Cl2, Br2, F2, I2, showing the outer shell electrons. 7 electrons share 1 electron, 7 crosses share 1 dot to complete the outer shell there. This is about simple covalent structure. We break the weak intermolecular forces between the molecules because these things have the actual number of atoms in one single molecule. So that means we have one single molecule, we have another single molecule. In between the molecule, we have weak intermolecular forces, therefore low melting and boiling points there. I'll probably just stop there for these lecture tutorials. I talk about a lot of stuff. It's time for you to digest some of these and actually write down a couple of things. And we'll talk more in the next series of these, in the next lecture of these predictable series of lectures. Okay, thank you for watching. Don't forget to click the button on the bottom right to subscribe to my channel. Follow me at ptet.chemistry on Instagram, Facebook, Twitter, and Telegram to get connected. I'll see you in the next lecture tutorial. Thank you for watching.